Professor Weavers, thanks so much for being with us on Little Lab Chats.
Well, thanks for coming to my lab. I'm happy to explore with you today.
Just last month, the EPA announced new regulations on 6 forever chemicals, also known as PFAS. You're an environmental engineering professor and you're co-director of the Ohio Water Resources Center. In addition, much of your research is focused on forever chemicals in our water. So first, what are forever chemicals? And then how are they getting in our water supply?
Forever chemicals are a group of chemicals, about 5,000 or so of these chemicals, that have been produced and developed in the 1940s. They were first developed for firefighting, and they were firefighting foams to put out oil-based fires on board ships, on board naval ships specifically. They also have a lot of other uses, like they are good for stain-resistant properties. They are very good for oil-resistant properties and grease-resistant properties, as well as water resistance. For all of those uses, that is how they've ended up out in the environment and finally in our water supplies. So they're found in rainwater all over the world. They're found in our blood, and they have health effects associated with them. There's certain cancers. There are things like high cholesterol and things that these chemicals interact with our endocrine system, our reproductive system essentially, and also our immune systems.
How is your lab tackling this increasingly pervasive problem?
So a lot of our research in my laboratory is looking at removing and particularly degrading compounds that are found in water systems. So these compounds are different in that they don't degrade in the same way as those other compound classes that we've looked at. They're just much tougher to degrade, and that's why they've gotten this tagline, forever chemicals. What we've been doing and studying is what's called ultrasound, which you've probably heard of ultrasound. But the frequency and the sound level, think of how loud it is what affects and causes these compounds to be broken down. Specifically, it makes what's called cavitation bubbles from the sound. And so those cavitation bubbles, when they grow and then they'll collapse, when they collapse, they compress the gas inside of them and it gets very hot. 10,000 degrees Kelvin, hotter than the surface of the sun. And so with that, we can break them apart by high temperature and break them down into components that are no longer toxic for us. So this is an example of a reactor that we're using right now in our laboratory. It's pretty small, hard to figure out how you're going to remove it from everywhere it is in the world. But it's a starting point, and this is where the sound is coming out of. And so that sound, figuring out how to scale up that sound and the conditions that are important that we think about as engineers, like cost, like how big and what does the energy levels need to be throughout the system, are the important pieces we're trying to understand to figure out, is it cost effective? Where are the best kinds of applications for this sort of technology?